Hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are again going to just begin our series in which we were just talking about six basic integrals proof actually. So, we successfully did the integral of, integral of sine of x dx, and the second one was cosine of x dx. So we successfully proved them out separately in the first video, and as I promised you guys, I will bring the second video on the proof of these two integrals, and then we will continue the last video on the proof of this very integral, that is the integral of secant x dx was secant x. We have to prove them down, and the integral of secant square x dx equals tangent x. So yeah, well, this has done, these two things has done already, had done actually, and these two will be done soon. And now we are just going to take a look at these two integrals on their proofs actually, with the same way that we did in this video. So like I requested you guys to just try this out by your own, and I hope you have tried, you must have tried this out, I hope that, and if you have tried that out, that's a good thing. Okay, so now let's just prove them down in this video. So we would just begin with our very first integral, which is the integral of e to the x time integral of e to the x dx. We have to prove this equals to dx, right? So basically we are having our small f of x, that is integrand as e to the x, and the result also that equals to e to the x, right? So basically we are just going to take the derivative of the capital F of x, that is basically d over dx of e to the x. So we're just going to take a look at the derivative of e to the x, and if it comes out to be e to the x, so basically this integral is valid, right? So yeah, from the definition of derivation of derivative, as I explained you in the first video, let me just do it right here even. F dash x equals limit h tends to 0 f of x plus h minus f of x over h. So this is the definition of derivative, right? So we are just going to plug f of x. We are just going to take a look at the f of x when f of x is e to the x. So let's just do that here. So basically it's f dash x equals limit h tends to 0. So when we replace x here with x plus h here, so that's going to give us e to the x plus h, and with minus the same function as it is over h. Okay, so yeah, now you can just take a look here. You can just notice right here, f dash x can also be written as limit h tends to 0. Well, we can just write this term as e to the x times e to the h. So e to the x times e to the h minus e to the x. And next, just take common the e to the x term. So it is e to the h minus 1 over h. And since e to the x is not depending on h, so it will be treated as a constant with respect to h. So hence it comes out to be e to the x, then limit h tends to 0 of e to the h minus 1 over h. Okay, so well, we have got our answer. We just need to prove this limit equal to 1, and then we are good to go. And how are we gonna do that? Well, we're just going to do here, we're just going to use the Taylor expansion of e to the x. So we are just going to use the expansion or the infinite series which represents e to the x. And now what's that? Well, it's e to the x equals the sum as n goes from 0 to infinity of, it's x to the n over n factorial. So basically we have to talk about e to the h here. So will be replaced with h. So e to the h is basically the sum as n goes from 0 to infinity of h to the n over n factorial. So now let's just replace e to the h with this infinite series here. So basically we are having f of x equals e to the x limit h tends to 0. This is the sum as n goes from 0 to infinity of h to the n over n factorial minus 1 over h. Next, what actually we just need to write it in expanded form in order to just get something better result. And let me just show you how it's done. Okay. So when you just expand that infinite series, right? So you're gonna have, we are having f dash x equals e to the x limit h tends to 0. So when you plug n equals 0, so that is 1 plus n equals 2, so that is, n equals 1, h plus h squared over 2 factorial plus h cubed over 3 factorial dot 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 to infinity, and we had a minus 1 over h. Now we can say this was positive one cancels out with this one. So we are having f dash x equals e to the x limit h tends to 0, right? And this is h plus h squared over 2 factorial plus x cubed over 3 factorial plus dot 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 to infinity over h again. And now what we're going to do is to just take h common outside the numerator's infinite sum. So that is f dash x equals e to the x limit h tends to 0. So when you plug h out of it, so it is 1 over h over 2 factorial plus h squared over 3 factorial dot 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 to infinity over h. And this cancels out with this h. And when you plug h equals h0 in all these on the places of all h's, so you're gonna have this one and all one is gonna be 0. We will be left with 1 only, and hence f dash x comes out to be e to the x times 1, which is e to the x. Hence proved, guys. It means that the derivative of e to the x is e to the x. So the derivative of e to the x is e to the x itself. That basically means integral of e to the x dx is also e to the x. And hence proved, guys. Wasn't that too amazing to prove that down? Because we ever use it as a memory power, yeah, we just need to memorize it, and yeah, we are good to go with the wherever we want to use that, right? But we never thought of its proof. So this is how it's done, guys. Okay, now we are having another one here itself, and I think, yeah, that is also going to be done with slightly similarly this, but slightly different, at least slightly different. Okay, so we're gonna talk about the second one. Prove that integral of a to the x dx equals a to the x over ln of a, where a is a constant actually, right? So, well, we have talked about e, right, in the last evaluation. But what about a? We had some expansions of e, but we don't know about a actually. Well, let's do something here. So since our f of x, that is integrand here, is a to the x, and the capital F of x, that is the result, is a to the x over ln of a. So we're just going to take a look at the difference derivative of this one, right? So if we take the derivative of capital F of x, that is derivative of a to the x over ln a. Since ln a is a constant, actually 1 over ln is a constant, so basically we are just going to take a look at this thing. Okay. Next, we're just going to do the same, use the derivative definition, and here we are having that is the f dash x equals limit h tends to 0, and when we talk about this one, so it is 1 over ln a, and it's a to the x plus h, right? And then minus it is 1 over ln a to the x over h. So we can just plug a to the x as well as a to the x over ln a outside this limit as a constant as we did in the previous integral. So yeah, let's just do that here. F dash x equals a to the x ln a, limit h tends to 0, and we are left with a to the h minus 1 over h. So this is the same result that we had earlier, but there was e over here, and we had an expansion of e, but we don't have an expansion of a itself. So now I'm just going to do some manipulations here. What's that? Again, oh my god, this thing that I'm going to use, I have told you multiple times to just keep it in your mind. What's that? Again, this can be written as e to the ln this. So basically for our case, this is a to the h. So a to the h can also be written as e to the ln a to the h, or it's e to the h ln a. If you want to talk about any function as an infinite series, so you just have to use this thing, and you are good to go with the expansion of e with this argument. Wow, that's really amazing. So here our f dash x comes out to be a to the x over ln of a, then limit h tends to 0. A to the h can be written as e to the h ln a minus 1 over h. And now we again here we have e to the h ln a, which can be written as an infinite series as n goes from 0 to infinity of h to the n ln to the n a over n factorial. Right? So now let's just do that here to get some better results, because directly we cannot do anything. That is why we need this kind of manipulations as well as some infinite series like e to the x. That is just helping us a lot here. So f dash x comes out to be a to the x over ln a, and then limit h tends to 0. That can be written as the sum as n goes from 0 to infinity of h to the n ln to the ln of a over n factorial minus 1 over h. So let's just write some of the first terms of this infinite series. So f dash x comes out to be a to the x over ln a, right? Next, limit h tends to 0. So when you plug n equals 0 here, so that is a positive 1. Then n equals 1, so it's h ln a plus h squared ln squared a over 2 factorial dot to infinity minus 1, like this is what this minus 1 I'm talking about here, and over h. Again, this positive cancels out with this negative sign, and when you take common h here again as we did in the first integral, so that is gonna cancel out here with this one, and again f dash x, when again we are left with h here. So when you plug h equals 0 in all the rest of these terms from here, so they are going to be 0. Basically we are left with a to the x ln a times ln a. So ln a then cancels out and we are left with f dash x equals a to the x. So hence proved, because we started with the derivative of a to the x over ln a in order to get a to the x, and hence we are here. So basically the derivative of a to the x ln a is a to the x. We have proved here, right here, and that proves integral a to the x dx equals a to the x ln a. Hence proved, guys. So that was all about these two integrals, and yeah, these two integrals consisted of infinite series in it, and more precisely it's e. With the first one it was directly substituted, but with the second one we did have to do some manipulations here, as you can notice, and yeah, it was good. So successfully we did the second video for that series also, and soon I'll just make the third video also, guys, and I'll upload it on YouTube channel. So yeah, if you got to learn something from this video, guys, please make sure to like, subscribe and share. And if you have any kind of doubt, any kind of issue with anything, please just share your thoughts in comment section. Thank you so much for watching this video, guys. Goodbye, take care, stay tuned for the next video. Again, I'm coming up with a lot of interesting videos, guys, don't worry.